Let's start by looking at this problem. We have 200 feet of fencing to enclose a rectangular plot. This is the rectangular plot, width and length. If you do not fence, so a plot that borders on a river, and we do not need a fence on the river side. If you do not fence the side along the river, find the length and the width of the plot that will maximize, in other words, find the maximum area. What is the largest area that can be enclosed? Typical type of problem, 66 on page 363. So here's the river, and here's the rectangular plot, and we have here x, and we have here x, and from this point all around the perimeter we only have 200 feet. We are limited to 200 feet. So obviously the 200 feet has to equal x plus y. So 2x plus y. That's how they came up with y being y equals 200 minus 2x. So they want us to find x and y, in other words, width and length, to maximize the area. So what are our options? Well, our options are these, or these, or this one. But we want to choose the maximum possible area. I don't know if this is the maximum. I don't know if this will give me the maximum area. I don't know if this will give me the maximum area. I want to find it. And I want to say to the farmer or my neighbor or myself, hey, with 200 feet of fencing, you should have this by this to guarantee the area to be maximum. If you use this by this, you're not going to have the maximum area. If you use this by this, you're not going to have the maximum area. I want to find exactly the width and the length that will make this area maximum. Since we're asked to maximize the area, I have to find an area as a function. I don't know how to find the maximum area, but I know how to find the maximum of an area that is a function. And I hope for a quadratic. Because if you give me a quadratic function, I know how to find its maximum. I know how to find the maximum. But if I don't have a quadratic function, I don't know how to find the maximum at this point. So, area. Can anyone give us the area of this rectangular figure? What is the formula for the area of a rectangle?
Length times width.
And excellent. In our case, the length is 200 minus 2x. In our case, the width is x. So I have a function. I'm no longer going to call it a. I'm going to call it f of x. And I'm even going to distribute. Negative 2x squared plus 200x. Always in descending order, because I want to be able to identify the a and the b. If the expression or the function is not in descending order, I may make a mistake. I may not identify the a and b correctly. And these are crucial. Okay, so again, let's recap. I have the picture. I don't have the length, and I don't have the width. but I want to create a maximum area. Because I want a maximum area, I have to find the exact width and length that will give me the maximum area. Nothing else will. Okay. If I'm asked to maximize the area, then I need a function. I hope for a quadratic that represents the area. Knowing that the area of the rectangle is length times width, that's where my starting point is. The area of this rectangle is length times width. I replace the width by, I distribute, voila, I have a function. Good. Does it have a maximum? Because if it doesn't have a maximum, I'm in trouble. Does it have a maximum?
Yes.
Because the leading coefficient is?
A negative.
Excellent. How do I find the maximum?
Negative.
Exactly, from the quadratic formula. Negative b over 2a. Indeed, negative. B is 200. 2 times a is negative 4. So I get 50 feet. 50. So this is my x. X must be 50. How much will y be if x is 50? If x is 50, how much is y?
100.
Yes. Feet. Excellent. I don't have to create any perform any calculations. What would be the area if it's 50 by 100? $50 by 100.
5,000.
Thank you very much. And this is in squared feet, and this is in feet. Done. Excellent. So if I don't use 50 and 100, I will never have a maximum area. Let's say 51. I will not get a maximum area. 55, I will not get the maximum area. The only setup, because there is only one vertex, only one point will give the maximum. So the maximum here is 50, 5,000. If I want to be here, it's not going to be the maximum. If I want to be here, it's not going to be the maximum. This is the only one. Only if I split the fencing 50-50 for the sides, for the width, and 100 for the length, I will guarantee to have the maximum possible area with 200 feet. Now, if you give me more fencing, it's a different story. But with this restriction of 200 feet, this is mandatory, 50-50 and 100, to guarantee a maximum area. Good. Anything else? A rectangular playground is to be fenced off and divided in two by another fence parallel to one side of the playground. So let's look at 69. Is 69 okay? And then we can move on. 69 okay?
Yes.
Okay. So again, it says a rectangular, fenced off and divided in two equal parts, or two parts, doesn't matter. So 69. So rectangular, x, x, y, y, and divided in two. A rectangular playground is to be fenced off and divided in two by another fence parallel to one side of the playground. 600 feet of fencing is used. Okay, 600 feet. This piece, this piece, this piece, this piece, and this piece will equal 600. What should I write on the left-hand side for all of them together? Can anyone tell us how to write the left-hand side? Because we're using the entire 600. So this, and this. What should I write in here to equal 600?
Y plus 3x equals 600 feet.
Yes, 2y plus 3x must equal 600 feet. Do you all agree with this?
Yes.
Perfect. Now let's read on. Find the dimensions, meaning x and y, of the playground that maximize the total enclosed area. And what is the maximum area? Again, we want to maximize this. Find x and y so that the area is maximum. Okay, the same thing. I have to start with the area. Can anyone give us the formula for the area of the rectangle, the total area? It's still x times y. Same thing.
X times y.
That's it, x times y. But I have a problem here. I cannot have two variables. So from this equation, I have to solve for y. In other words, from this equation, I have to get y and replace it in here. Can anyone tell us how to solve for y? The first step.
Subtract 3, both sides 3x.
Yes. So we have 2y equals negative 3x plus 600. And
Then
now,
you divide 2.
excellent. Negative 3/2 x plus 300. Good. So now I have the function f of x multiplied by all this. Of course, I have to distribute descending order. Negative 3/2 x squared plus 300x. Almost done. I have the function. I know it has a maximum. How do I find the maximum?
Negative b over 2a.
You're going to dream about this, right? We had it so many times. Good. Negative b, 300. 2 times a, negative 3. Negative 3/2 times 2 is negative 3. When I divide, what do I get?
Negative 100.
Careful.
Oh, 100.
Exactly. So indeed 100. How do I determine this? Very easy. First of all, let's find y. It's better and easier to find y. So x equals 100 feet and y equals. So let's plug in negative 3/2 times 100 plus 300. When I simplify, always simplify first. 2 and 100. So negative 3 times 50 is negative 150. Negative 150 plus 300 is 150. So 150, 100. That's the best and the easiest to do. So then this area is 100 multiplied by 150. 100 is the width, 150 is the length, and that's it. So 1, 5, and 3, 0. 1, 5, 0, 0, 0. 1, 2, 3. So and this is in squared feet. The area is measured in square feet, and this is in feet. So what should the dimensions be? 100, 100, 100, 150, 150 to guarantee the maximum possible area to be enclosed. So the dimensions of the rectangular area should be 150 by 100 to guarantee a maximum. Any questions? Okay, moving on. So this section 3.1 is completed. We move on to 3.2. 3.2 requires more time. We're continuing our exploration of polynomial functions. So other polynomial functions. Third degree, fourth degree. Okay. These are more sophisticated types of functions. Okay. Remember when we graphed the linear function, which is degree 1, we either had this shape or this shape. So this is for the first degree. For the second degree that we just finished a minute ago, we had either this situation or this situation. The third, the fourth, the fifth, the sixth, and so on and so forth will either follow this setup, and I'll explain what I mean in a minute, or this setup. So if it's the third degree, it will be in this category of the odd degree, not the odd function, symmetric or something. No, I'm talking about degree. And it will look, if it's the third degree, it will look like this, from negative infinity to positive infinity. Or it will look like this, from positive infinity to negative infinity. And this could be third, fifth, seventh, any odd degree. So what I'm talking about here is the ends. Negative infinity to positive infinity, negative infinity to positive infinity, positive infinity to negative infinity, positive infinity to negative infinity. Any odd degree, any polynomial that has degree 1, 3, 5, 7, 9, 11 will behave like this when it comes to the ends. This, or the other one. Of course, this one is when the leading coefficient is positive. Of course, here the same thing. And this one is when the leading coefficient is negative, and the same thing here. So if you're asked to graph any polynomial degree 3, 5, 7, or even 1, if the leading coefficient is positive, you will graph something from negative infinity to positive infinity. And if the leading coefficient is negative, something from positive to negative. You're going to see in a minute how this applies and where. What happens if we have second degree, fourth degree, sixth degree? This is what's going to happen. From positive infinity back to positive infinity, something like this, whatever. or like this, from negative infinity back to negative infinity, whatever. This is in the case of leading coefficient what? And this is in the case of leading coefficient what? These will be the same. These will be the same. A minimum is when the leading coefficient is
Positive.
indeed. We cannot talk about the minimum here, but this is going to be the shape. Coming from positive infinity and going back to positive infinity, from infinity to infinity. This one, indeed, with less than 0, from negative infinity to negative infinity, negative infinity to negative infinity, the leading coefficient must be negative. Same thing here, one more time, negative infinity to infinity, or positive infinity to negative infinity. Negative infinity to positive infinity to negative infinity. This is the first thing we need to establish. And this is called end behavior. So I'm asked, what is the end behavior of this function? Very easy. It's coming from positive infinity, going back to positive infinity. What is the end behavior of this function? Easy. It's coming from positive infinity and going to negative infinity. This is called end behavior. Okay. Number 2. So far, when we looked at the linear and quadratic, we didn't have to talk about this. But now, when we talk about higher degree, 3rd, 5th, or 4th, 6th degree, we need to discuss this. Initially, it was not necessary, but it's the same thing. Okay. Now, something characteristic to polynomials, something called multiplicities. What is this? Okay. We're going to look at a few graphs so I can explain. Multiplicities. Multiplicities refer to x-intercepts. And they can be odd or even multiplicities. Okay, so let's start simple. There is a difference here among these 3 graphs. This one has an x-intercept that does not repeat. There is only one, all of them have only one x-intercept, but there is only one value. So let's say x equals -3. Here, x equals -3 appears 3 times. And you can say, what do you mean, why 3 and not 2? I'll explain why 3 and not 2. Here it's even flatter. There is only one x-intercept, but it's even flatter than here, which means in this case, x equals 0 is the x-intercept, appears 5 times. How can this be? Okay, so here it is. This equation or function is f of x equals x plus 3. When y is 0, I get only one x equals -3. But what happens here is f of x equals x plus 3 to the 3rd. It still has only one x-intercept, but the same x-intercept, x equals -3, appears 3 times because of the power. And that makes the graph to be flatter than this. This is a straight shot, a straight cross. But this is a flatter cross. It takes its time. It gets closer and closer. It takes more time to get closer and closer to -3. And it takes more time to get away from -3. This one is f of x equals x to the 5th power. Because x equals 0, although it's only one x-intercept, it appears 5 times. It has five solutions, x equals 0. And you see, it takes even longer for it to cross. If I wanted to graph it so it's also here at -3, I would graph it like this. Slow, 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 finally crosses slowly, slow away from it. And this will be x plus 3 to the 5th power. This will be x plus 3 to the 3rd power. And this will be x plus 3. Notice that 1, 3, and 5. So odd multiplicity. 1 solution, 3 solutions the same, 5 solutions the same, and we can continue. So the odd multiplicity either goes from negative to positive, and of course I can have the other way from positive to negative. And this also deals with the degree, right? The degree is 3, the degree is 5, or degree is 1. So this is how an odd multiplicity looks like. Again, we have not talked about it because we didn't have to show multiplicities for a linear function. Of course, there is only one solution. And we didn't get to these functions yet till today. So we've never talked about the fact that there are 3 solutions the same, and then the function does not cross straight. It takes its time, and even longer for degree 5. So this is multiplicities and called odd multiplicities. Multiplicity 1, multiplicity 3, multiplicity 5. Again, m here is 1, multiplicity 1. M here is 3, multiplicity 3. M here is 5, multiplicity 5. I'm looking at the